Okay, this is the solutions tutorial for the 4A FIP quiz over sum of forces. On number 1, we say that 4 friends are having a tug-of-war over a turkey, and we're given 4 individuals and the forces that they're exerting. What's the net force on the turkey? So this puts together several concepts that you've been working with, such as finding sum of forces on each axis and resolving vectors into their components. Let's start off by drawing a free body diagram. So I'll start off by drawing in the forces that are on the y-axis. We have the force of Zach with 458 newtons due north, and the force of Kaylee with 364 newtons due south. Now we have a couple other forces that are not all on one axis, so we'll have to resolve them into their components. So the first of the 2 forces that we're going to have to resolve is the force of Jason, which we're told is 917 newtons at 47 degrees south of east. So knowing that, we can draw in the force of Jason on the x and the force of Jason on the y. So I've drawn in the force of Jason on the x and the y, and based on where this 47-degree angle is, we know that the force of Jason on the y is going to be equal to the sine of 47 times the force of Jason. Or, well, sine of theta times force of Jason, which would of course be sine of 47 times 917 newtons. So the force of Jason on the x will of course be cosine theta times force of Jason, or cosine of 47 times 917 newtons. Okay, now we're ready to resolve our last vector. We're told that the force of Hannah is 661 newtons at 35 degrees north of west. So we can resolve that into a force of Hannah on the x and a force of Hannah on the y. Of course, force of Hannah on the y will be our sine. So, force of Hannah on the y is equal to sine of theta times force of Hannah, or sine of 35 times 661 newtons. Okay? Force of Hannah on the x, of course, is going to be our cosine, or force of Hannah equals cosine of 35 times 661 newtons. Okay, now that we've got all of our x and y components resolved, we're ready to start with a sum of forces. I'm going to shrink some of this to make room for our math. So, with any sum of forces problem, with any of the problems in this entire first section, we always want to start with a sum of forces on each axis. So let's start with the y-axis, where things are relatively easy. Oh, I'm sorry, the x-axis is where things are easier. Let's start with that. So sum of forces on the x is equal to the force of Hannah on the x, which is going in this direction, plus the force of Jason on the x, which is going in this direction. When we figured out our magnitude for force of Hannah and force of Jason, by taking cosine of 35 times 661 newtons and cosine of 47 times 917, we got raw answers. So we have a sum of forces on the x-axis of 541.45 etc. newtons to the west. That's the force of Hannah on the x, plus 625.39 etc. newtons to the east. That's force of Jason on the x. So when we add them, and again, how you handle the signs here is up to you, whether you choose to use a conventional Cartesian coordinate system and assign values, or you choose to make the larger, oh actually in this case it's the same, if we choose to make the larger number the positive. What we get is 83.932 etc. newtons to the east. Now, time to do our sum of forces on the y. So when we list all of our forces on the y-axis, we have the force of Zach to the north, the force of Kaylee to the south, the force of Jason on the y, which is south, and the force of Hannah on the y, which is north. So we've got the magnitudes for those. Let's plug them in. Okay, so we have 458 newtons to the north, 364 newtons to the south, 670.65 etc. newtons south, and 379.13 etc. newtons to the north. So your sum of forces on the y-axis is 197.51732 newtons to the south. So now that you have your net force on the x and the y-axis, it's time to find your overall net force. And this is just a resultant vector of the two components given by your x and y. Let's draw the picture. So you can now see that the sum of forces on the y, the 197.5, etc., newtons to the south, and the 83.923 newtons to the east, given by the sum of forces on the x, form a triangle. And the net force overall is the hypotenuse of that triangle. So what we need to remember is that F net is equal to the square root of the force on the x squared plus the force on the y squared. When we compute that, we get a value for F net of 214.6109, etc., newtons. So with sig figs, that'll be 215 newtons. Now the question is, what's the heading? If we're going to use this angle for our heading, we see that the x dimension is our opposite and the y dimension is our adjacent. So if we use tangent, opposite over adjacent, we'll take the tan inverse of our 83.9, etc., divided by 197.5, etc., equals theta. So we get a theta of 23.022 degrees is our theta, and using the angle this direction, of course, that would be east of south. So it would come out to 23.0 degrees east of south. You can, of course, use the complement if you've arranged your sum of forces on the x and the y differently. So your final answer is 215 newtons at 23 degrees east of south, or its complement. That's the net force. Okay, on to the next problem. Okay, we're told that Tarek is building a catapult for lunch and home appliances and has to lift a washer over his head. So he has a mass of 75 kilograms and the washer has a mass of 156 kilograms. What we want to know is the force that the ground is exerting upwards on his feet so he doesn't plunge towards the center of the earth. Let's start off with our free body diagram. So first off, we have the force of gravity, which we know, of course, is mass times gravity. But in this case, it's the mass of both Tarek and the washer. So we're going to say it's the mass of T plus the mass of W, the quantity times gravity. Now we know that there must be a normal force exerted back upwards on his feet, and that's in fact what we want to find. So just for sake of form, we'll say sum of force on the x's equals 0, and we're not aware of any forces on the x, so we're going to move on from there. Now what we're really after is the sum of forces on the y. And we know conceptually that this has to be the force up plus the force down. So with that, we know that the only force acting up on him is the normal force, and the only force acting down on him is the force of gravity. And we know that since he's not rising up into the air or sinking spontaneously down into the ground, the sum of these two forces is 0. So now we can go about doing this. F of n is equal to the negative of the force of gravity. And we've created an expression for the force of gravity. So F of n is equal to the negative of F of g, and we have our expression for F of g right down here, the mass of Tarek plus the mass of the washer times gravity. We're now ready to the negative of that. So we're now ready to compute the normal force. So we now have our equation written out. The normal force is equal to the negative of quantity, 75 kilograms plus 156 kilograms times negative 9.81 meters per second squared. We get a raw answer for our normal force of 2,266.11 newtons. With 2 sig figs, we get a normal force of 2,300 newtons. Okay, our last problem is a force of tension problem, and we're told that Sarah is taking up the rings, and she has her young cousin suspended from 2 rings on cables that make a 38-degree angle with the ceiling. We want to know the force of tension on each cable. So let's start off with our free body diagram. So we're showing the 48-year-old young cousin suspended from the rings, and we have force of gravity directly down towards the center of the Earth, and the force of tension on each cable shown. Now, since our angle is with the ceiling, the easiest way to draw the force of tension on the X and the force of tension on the Y is out here, because it allows us to still use the 38 and not have to think too hard. And you know, not thinking too hard is a good thing. So here we see our force of tension on the X for cable 1, and here we see our force of tension on the Y for cable 1. Let's move this. Okay. So, we've got those labeled and established. Force of tension x1 will be equal to, I'm going to put it down here, cosine theta times the force of tension 1. So now let's do a sum of forces. We'll go ahead and do the sum of forces on the x, just in case, though we aren't going to need it in this problem. We know it's equal to 0 because the kid on the cables is not moving left or right, and we know that the only forces on the x-axis are the force of tension on the x1 and the force of tension on the x2. To get into the issue of the opposite nature of these, we can go ahead and say that force of tension x1 equals the negative of force of tension x2. But here's what comes up. Force of tension times cosine theta 1 is equal to the negative of force of tension times cosine of theta 2. This negative sign can be attributed to the fact that the angles are opposite to one another, though the magnitude is the same. So the magnitude of the force of tensions is equal. And this just tells us that force of tension 1 and force of tension 2 are equal. Once we cancel out those, so force of tension 1 equals force of tension 2. Now we're ready to deal with the y-axis, which is where we're going to get our real information. So if we're going to look at the sum of forces on the y, it's equal to 0, and we know that that's conceptually equal to the forces up plus the forces down. Now, let's start listing forces up. Well, we have force of tension on the y1 and force of tension on the y2. That's all we've got. And for the force down, all we have is the force of gravity. We forgot to note that that's equal to mass times gravity. I've gone ahead and plugged in the expressions that we've created for force of tension on the y, 1 and 2, and force of gravity being equal to mg. So since we know that force of tension 1 and 2 are equal, this is 2 times force of tension 1 times sine theta 1, because the angles are equal in magnitude, just opposite in direction. And that's all equal to mg. So we can solve for force of tension. Okay, so force of tension 1 is equal to mass gravity divided by 2 sine theta 1. When we compute, what we get is this. So force of tension 1, when we plug in all our numbers, looks like this. And it gives us a raw answer of 382.417, etc., newtons. So our sig fig answer, since we only have 2 sig figs to work with, is that the force of tension on each cable is equal to 380 newtons. Okay, we'll go over any questions you have on this in class on Monday.